Right, I think we are now live. Excuse me for this small delay due to technical problems. So welcome to the last day, the 5th day of the 11th OPTICON Gaia Science Alerts workshop, held online with participants from all over the globe. Thank you for joining. And without any further delay, I give the floor to Gaspar Bakos talking about HAT. Please, Gaspar.
Thank you. Good morning, good afternoon, good night, wherever you are. I'm glad to be here. I'm also happy that there was a little delay because I frankly was a bit surprised that I'm giving a talk. Somehow I missed it. But here we go. My screen is shared. I hope you see it. Please confirm.
Yes, we do.
Well, I'm hear you fine.
Good. And you hear me fine. So I just wanted to introduce here an instrument that is coming online very soon, and I think which will be highly actual for transient and high precision photometry. It's called Headbuy. It's an instrument which, let me switch slides, looks like this, at least in the engineering drawings. So this consists of 64 or 63 lenses and observes the whole sky above 30 degrees above the horizon. It has 63 CCDs underneath each of these lenses, and it's a fairly big instrument which will produce a 30-second cadence, if you wish, movie of the entire sky every clear night. It is stationed in Chile, and we were hoping to get it online sometimes in 2020, February, March, or April. But as you all know, other things happened and travel has been frozen since. So let me go back here to the specs just to summarize a bit. We have something like 23 arcsecond per pixel resolution. There's no gap on the sky. You observe everything above 30 degrees. Take an image every 30 seconds with all cameras. One key point of this instrument is very high per point precision and very low systematic noise. It's easy to monitor the whole sky in ways that are suboptimal, for example, with a fisheye camera. But what we're aiming for is moderately high spatial resolution and very high photometric precision. We have tested the lenses and CCDs now, and we can reach about 3 millimeg per point precision at V8, and the CCDs are back illuminated, and the lenses are fairly big and fast. Focal ratio we can see down to about 16.6 in R band in 30 seconds. Let me show you some cool things about it. Again, this is the whole thing. Now we are tracking on the sky. As you see, it's an equatorial mount. But as you can also see, we can't just turn around, otherwise the lenses and the whole thing would hit the concrete. So we're tracking for about 1 hour and then rewind and track and rewind. Now it turns out you cannot track the entire sky for obvious reasons. One is refraction. So you can't just optimally track on every point on the sky. Another reason is the warp of the mount or the improper polar alignment. So to remedy that, we actually, each of the lenses is held by this instrument holder unit, which is capable of an infinitesimal micro motion with respect to its standard position on the sky. So you can think of tracking on the sky as if it was a Taylor series expansion. We have the zero order, which is a sidereal rate track. And on top of that, each of these units has its own little micro motion with respect to the position. So basically every lens and every field of view can be sub-pixel position tracked on its own position. Why are we doing that? The reason is, as I mentioned, is the aim for very high photometric precision. And sub-pixel motions of stars lead to unwanted photometric noise. This is the building of Headbuy. This is at Las Campanas in Chile. It's a rollover roof building. It has a telescope bay. It has a computer room with all data processing happening on site, and has a small observer room. And the idea is it will open up every clear night and observe the whole sky. We have a very simple data policy, which is trying to make everything public. The overall yield is roughly a petabyte per year. We can't make yet all the images, everything binary, public, but the hope is to make everything that is a product, photometry of stars or selected stamps on the sky, public. This is a night image to show that we're not operating, but this is one that was taken during an instrument calibration run, unfortunately more than a year ago. And this is a Headbuy data flow summary showing how many row calibrated subtracted frames we get per night. I think what is important for the community here is a couple of things. One is we will try to do transient alerts. The second one is if you have a position on the sky that you think had an object of interest, even though there is no, say, Gaia source or any kind of existing source on that position, you should be able to retrieve a stamp of all images around that position and do your own photometry. The reductions have to be done on the side because the bandwidth from Las Campanas to the world is limited and expensive. So we're trying to do the processing as much as we can on site. And this is a summary, so I will give plenty of time for questions. We have simulated what we will actually see. There are three key science topics here. One is very high precision photometry and transiting planets. You may ask why transiting planets in the era of TESS, but as it turns out, by non-stop, meaning nighttime observing for multi-years, you can complement the TESS data stream in a meaningful way by significantly increasing its yield. But an interesting thing is that it will also provide light curves for many Gaia objects of interest where there may be an astrometric signature on the sky that indicates a planet that's along the line of sight at a big distance from its star. Our simulations show that after 5 years of operations, we have a decent chance of detecting a transiting planet that has a period over 1 year when we combine Gaia and Headbuy data. We've also figured how many transients we will see because, again, we see down to 16.6 in 30 seconds. So the numbers are shown here, about 10 novae per year, about 100 supernovae per year, and hopefully some electromagnetic counterparts of gravitational wave detections. It will have a unique spot in the existing parameter space through its large field of view, very high precision, decent spatial resolution, and short cadence. Our faint end is roughly where LSST is saturated. So it will also nicely complement that. And at this point, I will stop. There's still a couple of minutes left, and I'm happy to, I don't know what the system is for questions, but I'm happy to answer whatever you have. And I want to mention that I'm very keen on looking for collaborations, and we're also advertising a position for managing the data flow at Princeton. Thanks, everyone.
Okay, thank you very much. That was very inspiring. Simon has a question, please.
Yeah, it looks lovely. It reminds me an instrument called Fly's Eye. Is it connected or grown from Fly's Eye?
It's not connected to Fly's Eye. I'm aware of Fly's Eye.
Concoli, I think.
Yes, it is in Concoli. It's in Hungary, developed by András Pál. Fly's Eye has shorter focus lenses, less of them, with a coarse resolution. It's on a hexapod, which is an ingenious way of tracking the sky for short instances. I trust our photometric precision will be far better, and our spatial resolution is much better. They're different instruments in terms of their scale, but there are some things in common, which is observing the whole sky.
Yeah. The serious question I had was, is your transient detection, is the plan to stack the images and run it as an hourly cadence, or are you doing the high cadence shower, or a combination of these things?
We plan to do the 30-second cadence image subtraction, and I'm keen on looking for very fast transients, because I think that's a niche which is not fully explored. So either transients which have very short time scales, meaning a couple of minutes, or transients which are very small in amplitude, or transients which have features that are very small in amplitude. For example, or the little wiggles on top of a nova light curve.
Yeah, beautiful, good.
So I have there is a question regarding are there plans for northern hemisphere? Do you plan to have a twin somewhere in the north?
Oh boy, I think with the momentum I had a year ago, I would say yes, but now I would say I'm just happy to get this done,
Right.
and then we'll see.
Okay, and my question is, I'm personally interested in the galactic plane. Are you going to avoid it or observe it, or what do you expect for the galactic plane?
Once you have a field of view of 1 pi steradians, you can't avoid the galactic plane.
Yeah, exactly. Yeah.
So no, I love the galactic plane, and through the image subtraction we're doing, we're getting very high precision photometry also for that. I have to add that the stellar positions are, after an astrometric transformation, are projected onto our images from Gaia. And thus we can technically carry out photometry for any Gaia source down to something like 14 with 10% precision. And so that we'll just do it as other parts of the sky.
Mm-hmm. Excellent. That's going to be extremely useful for our microlensing candidates we keep finding in the galactic plane.
Yeah, I'm happy to. Again, the idea will be sharing as much as we can share, given limits of person power and bandwidth and other things.
Okay, great. I just add that I've been visiting Las Campanas over the last 20 years very frequently while observing on the Ogle telescope, and I did see the old hut dome, the robotic dome operating there. It was fun to see it closing in the morning. So I
it's
remember
still
this.
operating. We have 8 other telescopes running at Campanas, head south telescopes, and those are running every night. So
right,
we have a little hat village now on the mountain, and I'm glad to see Polish astronomers around with all their kindness.
Great. Okay, thank you, Gaspar. So we move on to now a series of brief talks. Remind the speakers that these are poster talks, right? So essentially you have 3 minutes to present 1 or 2 slides very briefly, so to leave time for some discussion afterwards. Josep Manuel Carrasco goes first, please.
Yeah. Okay, I share my screen. Okay, this is a short talk, as Łukasz was saying. This is just a reminder that we are around. We are observing from this telescope, the Joan Oro telescope. It's an observatory that we have in Catalonia, in Spain, in Lleida. And it's the only place in the Catalonia territory which is dark enough to perform high quality astronomy. And this is the observatory we have there. It's an international observatory. Everyone can request for time. But it's a starlight reserve area. So it's a dark sky place. So, and the telescope we are using is this one, the Joan Oro telescope, is this dome here. Here we have another telescope, but the one we are using is the Joan Oro telescope, this 80-centimeter telescope, which is totally robotic. So every day you can select the new target for the next for the night, and there is an automatic procedure to select among the different proposals, prioritizing as if it was a printer, and you have a queue of programs, and it chooses the perfect time to observe every target during the night. And this is chosen every afternoon, and then you recover the data in the morning, completely robotic and without anybody there. So you from home can select the targets and retrieve the data the next day. This is the good thing, that it's a small telescope, 80 centimeter only, but it's totally robotic. And it has 2 weather stations and 1 storm detection system to detect the storms, and in the case it's needed, then close the dome and stop the program and resume afterwards. The instrumentation that we are using is the imager. Gaia imager is a CCD for which you can use several passbands. I will, the Johnson passbands, the normal ones. It's a 30 R minutes field of view. You see here this dark spot, it's the spectrograph, which we are not using. I will explain you why. This is a camera with 4,000 times 4,000 pixels with a pixel size of 0.4 arc seconds. And this is the spectrograph. And I was saying it's difficult to be used in this program because it has a very bright regime. At magnitude 13, you get signal to noise ratio of equal to 10 if you integrate for 1 hour. So it's difficult to get information for the science alerts. Only the most brighter, and I think none of them are in this range. So we are not using the spectrograph, but it's available if you are interested with other programs. And this telescope has been devoting time to the science alerts from Gaia since 2015. We are observing in 4 Johnson passbands from V to I. In every of these passbands, when we choose a target, then we take 3 different exposures for every passband. And doing this since 2015, we have reached 75 Gaia alerts, following up these alerts, and obtaining a lot of images because we use 4 passbands every time. So we have collected 21,000 images to the program in the calibration server. This is according to what I saw in the table of contributors in the Cambridge server, calibration server. Ours is the 3rd most contributing observatory. What is the strategy we choose? We perform to select the targets. As it's a small telescope, we need to observe the most brighter objects. So we start observing a target when having a magnitude brighter than 17.5, something like this. And we can continue when the alert gets dimmer, and until magnitude 19, we are able to follow up this target, every target. So this is the distribution of the 75 Gaia alerts we have observed until now in the sky in galactic coordinates. And well, among the targets, the most famous targets that we have contributed with observations from MONSEC are these 2, which you know very well, and they have been explained earlier in the meeting. So, well, it's nice that we have two papers with this data. We have granted time for this semester until summer. But every time we submit a new proposal, the time allocation committee says that we need to produce some results from these observations. So we have observed 75 targets, and we got 2 papers. So then 73 more papers are waiting for us now. The problem is that we are not experts in neither microlensing or TDEs or supernovae. We started with supernovae, but we are now focused more to observe microlensing events. But this is a call for you that if you want to use our observations for your scientific purpose, then we are open and available to you. If you want to drive us to some specific type of alerts or any suggestion, it's welcome. And you have here my contact to contact me and ask your request. Okay, that's it.
Okay, thank you very much, José Manuel. There's a question from Yair. What filters are available, and are you planning to do gravitational wave follow-up? That pays better in papers, I must be honest.
Sorry?
There is more papers coming out in gravitational waves than microlensing recently, but we're working on it. And that's why Yair is trying to tempt you with gravitational waves.
Yeah. We are really open to if you think that the magnitude range is suitable for your purposes, then you email to me your targets or your preferred observation mode and things like that. And the passbands we use is, as I said, we have the Johnson passbands. We also have the U passband, but we are not using it because the response of the detector is quite low in that range. But B, V, R, and I are observed. When I perform observations, I do it in all 4 passbands.
Okay. Thank you. We should move on. I can leave the discussion between 2 of you in the chat or WonderMe. Let's now move to another talk, short talk by Marco Lam. Please, Marco.
Hello. Can you hear me and my slides and my cursor?
Yeah, everything seems fine. Yes.
Okay, excellent. Thank you. Hello. Good morning, afternoon, or evening, depending on where you are. I'm Marco from Tel Aviv University, and I'm going to talk about the spectral data reduction software that I have been developing in the last 2 years. And so it started off as a joint Liverpool John Moores University and University of Warsaw project funded by the OPTICON. So thank you very much, OPTICON. And then it was transitioning through the University of Warsaw over the difficult time last year before I finally arrived at Tel Aviv and now continue to develop this software and try to integrate it with various systems. And I will mention it in a bit. The main motivation for this project is that there's a discontinued support for the IRAF software, which is used to power a large number of data reduction tools. So, and also there's also a shift in the software paradigm in the last 30 years, with a very large popularity among with Python among both the users and the service providers, for example, Asteroid. And we are also looking into greater cross-platform and interactivity from the software. And we decided to develop a new set of routines to hopefully replace at least some of the functions available with IRAF. And so instead of building a pipeline specific to one instrument, we are developing tools that are as general as possible so that users can easily tailor their pipeline with simple coding efforts. And so I'm not going to talk about this technical slide. So if you're interested, please come back to the recording or talk to me afterwards. And same goes for the details of the data reduction. And I will only stress that we are able to perform simultaneous spectral tracing, but we can't do simultaneous extraction just yet. We plan to, but it is not yet available. And same goes to the 2D distortion correction. It is actually very high on our list, but it is not ready to do that. And a second thing is, we are storing all the standard spectra available from IRAF and also those available from the ESO and ING web pages in the software, so you don't have to figure out how to compare them. And so currently there are 3 potential deployment instruments: the Spread Undeliverable Telescope, the Mukodi to be installed on the CD telescope, and also a new spectrograph to be installed on the 1.93 meter telescope in France. And on top of that, we are also testing the reduction on a few other instruments unofficially. And for the Spread instrument, we are currently in the commissioning phase. This is one example of the diagnostics that we are looking at. So on the left, it shows the spectra reduced with the new pipeline, and on the right is the old. So the main improvement you see here is that we are using optimal extraction and also doing cosmic ray cleaning. That's how you see the improvement in signal to noise so clearly, even by eye. And for this second plot, we are overplotting the sensitivity curves used for flux calibration from 200 calibration with the new pipeline, and compared to the dashed line, which is from a single manual calibration with IRAF. And again, they are showing very good agreement. So what we have to do, we are left to do with the new pipeline is basically to repeat these kind of experiment on analysis on different observing conditions, and also because the telescope itself is robotic, so we need to make sure that it does all the error trapping properly. And as of this week, we have released version 0.3, and the version 0 status means that the API is still subject to quite a lot of changes. However, the most commonly used functions are largely stable by now. And so as long as we are doing something mainstream, then yeah, the software should be able to cope. And we will continue to employ as many automated processes as possible to aid the development. And we are expecting updates every few weeks to months. If you want more information, I would recommend you to go directly to the GitHub page, where you can find all the links to the references where the software is, and also how you can install it and the documentation and everything. So yeah, please come to talk to me if you want to contribute or use it. Thank you.
Thank you very much, Marco. I think we will have to move the discussion to chat. I see some people are interested. So while we switch to another speaker, I will just mention that while Marco was working for us in Warsaw, we hope to have his code integrated into our Black Hole Tom. It's not there yet, but we're working on it. So eventually our Black Hole Tom will also be capable of processing spectra from multiple telescopes. That's the plan. Thank you, Marco. Let's move on to another talk presenting a telescope from Malta. Stephen.
Hello, greetings from Malta. Do you hear me?
We can hear you, we can see you, but we don't see your screen yet.
One moment. Okay. About now?
Yes, that's it. Mm-hmm.
Okay. Greetings, good day to all. I'm an amateur astronomer from Malta. Malta is a tiny island situated just below Sicily in Italy. And my location, my observatory, Flare Star, is located at San Juan at an altitude of 110 meters. I started operation in 1999 as minor observatory code 171, where I have done astrometric and photometric observations of asteroids. Here's my telescope. It's a 0.25 meter Schmidt-Cassegrain telescope that is remotely controlled and can operate all night long without any intervention from my side, except that each night I have to open or close the observatory for every observing session. I've installed some fail-safe devices included to prevent some mishaps such as rain or clouds. To substantiate such precautions, I've also installed 2 night vision cameras for remote monitoring. Up to now, I have conducted over 98,000 variable star observations, mostly of cataclysmic variable stars, and an additional 15,000 K asteroid observations. Well, as you can see, my telescope is rather small, but I am in the process of right now of increasing the observatory, as I have ordered a larger one, so I would enable to install a larger instrument. Here are my observatory parameters. I use a Moravian CCD camera with a field of view of 25 by 17 arc minutes with a pixel scale of 0.98 arc second per pixel. Most of the work I conduct is carried out through visual, V, and infrared fluorescence I bands, and also employ neutral filters, as well as the clear blue blocking for exoplanet work. Well, I process all of my images through MPO Canopus, where I process all photometry and also analyze the light curve through this software. The operational mode I conduct are usually pre-adjusted before every observing session, but I can intervene from the physical site of the observatory as well as through remote operation. Okay, regarding night sky conditions, they are not the optimal ones that most observatories on mountaintops have, but nonetheless, some good work can be conducted even though light pollution is rather quite moderate at my site. From the weather side, Malta enjoys a good share of cloud-free skies. And as you can see, there's a lot of clear skies available throughout the year. However, during the winter times, sometimes weather conditions prevent the observatory from being operated for a number of days. However, during the summer months, it's usually always clear. The best conditions for seeing, on average, I have at 2.5 to 3.3 arc seconds per pixel. That is not so bad considering that my altitude is nearly at sea level here. Well, the light pollution map on the right-hand side shows the light pollution intensity, and it shows that my north to west skies are the most clear. Nonetheless, you can always work around by employing longer exposures, perhaps, to gain the sufficient signal to noise ratio to get good results. Well, my observing programs is rather diverse. I mean, I follow up cataclysmic variable stars most of the time. I have also now done some microlensing observations, and about 30 to 40% are conducted for asteroid photometry. Exoplanets has also now been introduced into my observing program, which are followed by variable star discoveries. I have a very small number, and some in-depth monitoring of some stars that were discovered. Well, here's my light curve at the top right corner of Gaia 16 AYE. That was my first intervention with microlenses, microlensing, and it shows that my data is in line with those of other observers. Okay, this is a typical light curve of a cataclysmic variable that I usually observe from my site. Here we're seeing super humps. I usually do exposures of less than 2 minutes, so I would be able to determine the period of the super humps that are related to the orbital period of cataclysmic variables. Such observations are usually conducted after I receive a notification from alert notices, or sometimes through direct requests by certain astronomers. Well, here's my observation again of Gaia 16 AYE. I have a number now of images of Gaia targets that are ready to be uploaded soon to the BH DOM. Thankfully to Lucas and to Powell for giving us the opportunity to do so. Regarding asteroid photometry, I started in 2000, and I observed these to derive the rotation period of these asteroids. During the same year I started, I initiated a collaboration campaign with Robert Koff that I have become to know that it was the first international collaboration in the asteroid field. Most of my targets that I choose are usually with unknown periods. So because such work, I find that it's more interesting and perhaps even scientifically more variable. Due to my aperture limitations, I usually track down asteroids brighter than 16th magnitude, but through 60 to 240 second exposures. But sometimes I expose for longer to gain the sufficient signal to noise. Nearly half of my campaigns on asteroids are conducted through collaborative campaigns, and also all results are submitted to the Journal of the Minor Planet Bulletin. Up to now, I have managed to determine the rotation periods of 55 asteroids, and also participated in campaigns such as the one for Reginita shown here, to derive the asteroid shape. Regarding exoplanets, I have conducted some experimental tests to see if I could autonomously go after exoplanet transits autonomously without my intervention, and manage to check whether my system is capable of such work. And the results have shown that my observations are quite reliable. That prompted me to join the Exoplanet project. That is a project to support the aerial mission for exoplanet investigation. The aerial mission is a European Space Agency satellite that will be characterizing exoplanets, and in support for this satellite, amateur astronomers and other astronomers can contribute to this project to update the ephemeris, so the satellite would home in at the correct time to observe these exoplanets. Below are some light curves that I have conducted for the exoplanet project. And these are the variable star observations, discoveries that I managed from my site. These were not conducted specifically, the searches, but were just an offshoot from the photometric asteroid work, where each night you have to image a different field. So I data mined the images and found the following variables, stars, new variable stars within those images. Such work is conducted also through an informal group that I have, where we collaborated with each other and produced 3 scientific papers on some of the variable stars that we discovered and on the reclassification of a Cepheid class, of a Cepheid star to a UG class star system. At the left panel, you can see the observatories that my colleagues own. 2 others, Antares and SNIT, are located in Malta, while the observatory is located at La Palma and use a half-meter telescope. Currently, we are conducting a research on one of the variable stars we've discovered, and ongoing research has managed to derive the modeling of the binary star, as the star is also has RS Canum Venaticorum characteristics. We also extracted data from the Assassin survey to check the variability on the long term. Our time of minima conducted along some years show that there's a period change, but further observations are being collected at this time. We have also done a flare monitoring campaign of the system where we have managed to reveal 2 flaring events. I wish to conclude by stating that variable stars provide an optimal opportunity for amateurs to contribute to the professional work you are conducting as professional astronomers. We have, as amateurs, we have the capability to alter our program readily. So we are ready, we are always there to observe any transient that is an outburst or active. And thanks to such collaborations, my venture in photometry has yielded over 40 co-authorship in research papers with professional astronomers. Well, that's it, I believe. Thank you for your attention. That's it.
Thank you very much, Stephen. I would like to emphasize the work done by Stephen and all the amateur astronomers. The devotion they have, it's often much greater than the professionals have. So, and that pays off in beautiful data and long time series, amazingly long time series. It's very hard to get otherwise. So thank you for this. Are there any quick questions to Stephen while we change slides to Michel Dennefeld? I will stop sharing your screen. If we can have Michel.
Yeah.
Okay. Yes. Let's move on to keep up with the time. Michel, please share your screen.
Yes, just a second. I'm sorry. I have to. Where is it? Here. So do you see it or no?
Not yet.
Yes, okay. Why doesn't it work?
Yeah, there's something coming.
Okay.
Yeah, we do see your screen now.
Okay, good. So I will talk about follow-up of some Gaia alerts, which are not only supernovae, The supernovae are part of the PESTO program. In fact, nobody was talking about this one, but fine. And I will divide my talk in two parts. On one hand, some older Gaia objects, that is the first alerts in the first years, and the second part, I will show you a few examples of more recent ones. Can I have that? Yes. So we have compared all the Gaia alerts from the beginning until the end of 2018 with archive spectra, both from LAMOST and from Sloan Digital Survey, and we included in that comparison also the nuclear transients from Susanna's paper, which covered a 1-year period. The 3 arc-second search radius and the spectral range of these surveys is covering from 3,700 to 9,000 angstroms. But of course, one has to be careful that the spectral date is usually very different from the alert date. So it's not necessarily the alert stage that you see. Concerning stars, we found 26 spectra which were classified as stars in the archive, and among which 12 had multi-epoch spectra. Most of them were cataclysmic variables, which are easy to recognize in the low state, but less so when they are in the high state because the system is optically sick. So here you have one example of Gaia 15 ABY, which is a cataclysmic variable where you recognize from the emission lines. And here is another one where we have 2 different epochs. One epoch, which is in the low stage where you see the emission lines, and in the high stage, you don't see anything. So a spectrum like this one would unlikely be classified as a cataclysmic variable at the time. And we have some examples of spectra which are classified as stars, but which may be cataclysmic variable in their optically sick stage, like this one. What I'm surprised is we found exceptionally only young stellar objects, and I don't understand that. We may discuss with respect to Simon's presentation on the first day, where he separated cataclysmic variable from young stellar objects in the color magnitude diagram. For galaxies, most objects were emission line galaxy. We have a few absorption line galaxies, in total 206 Gaia alerts, among them 49 with multi-epoch and 55 in Susanna's sample, 13 with multi-epoch, and a few Seyferts. But of course, the problem is that in Sloan or in LAMOST, many galaxies have not been recognized as Seyferts because they are only Seyfert 1.9, that is only a weak broad H-alpha component, which I will show to you. And of course, there are starburst galaxies likely to provide supernovae, but AGN activity is there also, and I will show you quasars in a few moments. And you need a light curve to distinguish. So here is one object which is clearly a starburst galaxy, and I would like to emphasize this feature around 4600, which is characteristic of Wolf-Rayet stars. And when you look at the Gaia light curve, it's obviously a supernova type light curve, although it was not catched spectroscopically at the moment of the explosion. So it's consistent with the host galaxy. We have found only 2 objects where we could confirm the supernova with the archive data, because by chance the archive spectra were taken only a few weeks around the maximum. On the left, you see the GNT object, where by subtracting the one here, LAMOST spectra, the SDSS spectrum, you get a result spectrum which has been classified as a 1A supernovae around 2 weeks after maximum. And on the right side, you have another object where it is a 1A roughly around maximum, but you have only 2 cases like that. Some misclassified Seyferts, as I said, but it's not clear there whether the alert is due to a supernova or to genuine AGN activity. We found a few Seyfert galaxies where star formation is known to be present and therefore could be supernova also. Here is an example of an SDS galaxy which was classified as galaxy, but you see clearly the broad H-alpha component, but nothing at H-beta. So this is clearly a 1.9 misclassified one. Here another example where the broad H-alpha is even smaller. And another example where again you have a very faint broad H-alpha component, but strong oxygen tree here. So the Seyfert component is not dominating the galaxy. Now, of course, this is due to the classification in the archives, which classify the objects as galaxies, but we have, of course, many classified as quasars, 30 in the Gaia alerts, 68 in the Neutral Transient Center, plus 12 and 23 with multi-epoch spectra. So this is the interesting part, I think, of this work. When you have a variability in an AGN or a quasar, it's difficult to know a priori if it's a supernova, target disruption event, or AGN variation. So we need the light curve to complement. And when you have multi-epoch spectra, allows you to detect variations, and we have a number of changing look quasars or changing state quasars depending on the name you want to use for them. And we found, confirming what has been known from other surveys independently of Gaia, that the H-beta broad component increase is generally going with also an increase of the blue continuum. Now, the good question, where we have no answer yet, is what is the physics behind that? And of course, you need spectra coincident with the photometric change and also a long-term monitoring to be able to understand what is happening there. And the one relevant question is also from the Gaia alert, what is the delta magnitude level you have adopted for alerting or not? Clearly, this has been changing over the years, and it makes it difficult then to follow up statistically the number of objects. I will show you soon. So here is one interesting example, Gaia 17 boom, where we have 3 Lamos spectra taken a few weeks interval, and you see between the lower one, which is the earlier one, and the next ones, the magnesium 2 component is getting stronger, and the H-beta component is getting much stronger also. And when you compare with the Gaia light curve, here are the dates of the 3 spectra, which were of course taken randomly, and the spectra appear before you have the photometric increase. So it's not clear whether this change of spectrum is due to a previous increase of luminosity or whether the luminosity increase seen by Gaia is the consequence of the change of spectrum. So what we need, of course, is monitoring objects like that more regularly so that we have spectra close to the different maxima. You know, this one was alerted much later. In fact, it could have been alerted here. I don't know why it was not at that time, but there are many examples like that. So now we have some more recent examples. I show you one which was of June last year, which has shown a rise of 1 magnitude over months. The Sloan reference spectrum says a liner, and the object is high since then. So here you see below the reference Sloan spectrum, which has maybe a very faint broad H-alpha component, so it would be a Seyfert 1.9. And the recent spectrum, clearly you see a strong increase of the broad component here. So we need a better sampling to understand the origin. There are 2 hypotheses which are at the moment under study by various groups. One is an increase of the accretion rate of the quasar, and the other is a change in the reddening. Now, the change in the reddening, if you take simple models, say a broadline cloud orbiting around the central continuum source, you can calculate what is the time scale. If you take a very small central engine, typical from the X-ray source, you would get a time scale of days for the crossing time around the Keplerian orbit. If you take the much wider broadline region in general, the time scales would be rather years, which is clearly not the case for the Gaia alerts. But of course, these are very simplistic models. And my suspicion is that the torus and the obscuring region around the AGNs is a composite of many smaller clouds. And from time to time, you have a hole in between where you can see the central engine. And if this is correct, then once you are in a high state like the one I'm showing here, the object should go down again after once the obscuring is coming on again. So clearly monitoring is needed. That is spectroscopic follow-up with many instruments. I show you some more examples like that. So here is one example, but probably here you have a change in the accretion rate. Here, similar, probably a change in the accretion rate. We don't know because spectra we have taken only very recently when the object was down again. But here is another interesting object where the object has increased end of 2019 and stays high. And another one like that, where you have a slow increase and still high at the moment, where the explanation could perhaps be rather a change in obscuration rather than a change in accretion. Just as a reminder, the standard model for a Seyfert galaxy is that a Seyfert 2 is in fact a Seyfert 1 where you do not see directly to the central engine because of obscuration. So clearly obscuration is playing an important role in active galactic nuclei. Otherwise, the standard model may have to be dismissed completely. So to do follow-up, we need, say, typically 2-meter class telescopes or larger. We do classification of older objects. For instance, we have obtained, say, last month, spectrum of Gaia 16 BPI, which was a candidate AGN according to the ALERT website. And if you, that is the light curve of 16 BPI. And if you see the spectrum we have obtained, well, that resembles more a BE star, maybe a young stellar object. So clearly one needs to come back also to older objects to clarify all that. So to do that, as I said, we need 2-meter telescopes or larger. Some of them are used at the moment, the Nordic Optical Telescope, Asiago, and at Haute-Provence now we are constructing a new spectral imager, which is under test. It's a modified copy of the Spratt Liverpool, where we got the drawings thanks to Jan Stiele, and the reduction software will be adapted from Marco Lam, who's just presented his thing before. This spectral should be there since years, but for various reasons, it's coming on only now. We are hoping that it should be available for general use end of this year, but of course there are already test periods now, and so if there's something very urgent, we can always accommodate it. Just to show you one example, that's the instrument hanging permanently at the Cassegrain focus of the telescope, where the main instrument is a fiber-fed high-resolution spectrograph for exoplanets, so you can switch from one to the other within something like 15-20 minutes in case of an alert. This has to be automized still, but it's working. And here is a first spectrum which I obtained last December. This is in the red setting, going from 6,000 to 10,000, and it's the well-known Theta star. I have taken that as an example to show you the strong calcium infrared triplet in emission. The calcium infrared triplet is very important for Gaia aficionados. And I was wondering whether you can detect this calcium triplet in emission with only the red photometer of Gaia. I have not seen many alerts, to say probably none, where the calcium triplet has been detected in the red photometer. I don't know if somebody can clarify that. So as a conclusion, we have a lot to do. We need a lot of spectroscopic time. And of course, you need to react rapidly depending on the type of target. Minutes for gamma ray bursts where Gaia is not competitive. Hours for supernovae, okay, maybe, but in many cases when Gaia alerts an object, it has already been detected by other surveys because of the reaction time of Gaia. So the study of AGNs may be one thing where Gaia can have a very important role. And in particular, to distinguish tidal disruption event from AGN activity, you need follow-up. So to answer Simon's question on the first day, I would say more Gaia alerts will certainly be welcome, although we don't have enough telescope time to follow all of them. But if you separate clearly what is a good alert in your opinion and what is a less good alert, then we can select those to be followed. But the important point to me is that once you have an alert there, you have the light curve, which is followed up regularly. And then with time passing, this will help to distinguish what type of alert it was indeed, even if you don't get immediately a spectrum. So I would encourage you to give more alerts, but separate them from the regular good ones. Thank you.
Thank you very much, Michel. That was very inspiring. Are there any quick questions to Michel now? I don't see any, and I suggest we can find Michel now, I hope, in the Wonder Me. So I would like to announce the break. Let's make this break last a little bit longer than planned, so I updated the agenda already. So let's meet here again at 4:20, 16 hours, 20 minutes, Polish time, Central European time. So in something like 17 minutes. Okay, and I'll paste the Wonder Me link here in the chat so that you can go there and talk to Michel, all the previous speakers, and everyone else. Thank you, and see you in 16 minutes.
Hi, Michel.
Hello, John.
Good to see you.
Yes, it's the same for everybody. In fact, in this confinement period, it's good to see people. Yeah.
Yeah, it's completely crazy. I've been in the office 5 times, I think, since March, maybe 6, but you know, you can count them almost literally on your fingers in 10 months. It's ridiculous.
Yeah, I was lucky to be able to go to the observatory 2 times in the last months, but not in Chile, unfortunately.
No, my passport's about to expire, and you know, it expires in February, which means it's practically useless now because everyone wants 6 months.
In a few years, Scotland will be part of Europe.
No, don't start. Please, let's keep politics out of this. You're still flying?
Well, not at the moment, because in the confinement or semi-confinement period, we are not allowed to be closer than 2 meters
Yeah.
in an airplane, you know.
Yeah.
Although, in fact, when I fly with Air France, I'm shocked to see that they are filling the planes completely, so you are packed as before, you know, despite the separation measure you should have.
Yes, it's all completely crazy. The people next door to me, to my house, her mother just died. They just had the funeral today. I mean, how can you have a funeral when you can't, you know, you can't have people with you? It's terribly sad.
Yes.
Right. Okay. So we're starting again in 15 minutes. Is that right?
Yes, apparently, yeah.
Yeah. Okay, good. Well, I'm going off camera, but I will be here.
Yeah, yes, me too. See you later.
Bye.
We're slowly getting ready. Can I ask the next speaker, Goran Damljanovic, to set up his screen, please?
Okay.
Well, when it's all working, then we will start, but it's 2 more minutes to start.
I can start?
No, wait, 2 more minutes, but
Okay.
just share your screen because we don't see it yet.
It's okay?
No?
Okay.
Okay, that's better.
Okay, yeah.
Yes, this is better. Okay, so if you're ready, then I think we can start in the last remaining session of the Gaia Science Alerts workshop. We've got Goran Damljanovic presenting the Gaia Alerts and the Serbian-Bulgarian mini network of telescopes. Please, Goran.
Thank you. With a few colleges in Bulgaria and in Serbia, at the beginning of that project, during 2013, we started the test phase of Gaia Alerts project, and after that,
I'm sorry, but we cannot hear you anymore. I thought we lost you, sorry.
You see my image, huh?
Yes, we do see your slide, your first slide, yes. Maybe you can just scroll down. I think if you hit the arrow down in the circle here, it will show the next page, and that should be fine.
Okay. Sorry. And okay. And after that test phase during 2013, we continued with the alerts during the second part of 2014. Also, we did about with a few colleges here about astrometry during in that Gaia mission project, and it's important to mention maybe if there are some colleges interested about that about astrometry. We are doing a link Gaia Celestial Reference Frame CRF and International Celestial Reference Frame using the quasars visible in both optical and radio domains. We are doing investigation of flux variability and morphology of that extragalactic objects important for that mentioned the link. And also to do that part of Gaia observations, Gaia alerts, we established the
local cooperation, Serbian-Bulgaria mini network telescope at the end of 2013. And here, just to mention that at the beginning, during 2015, just less than 200 alerts started with less than 2,000 alerts, but now about 200. Now it's about 4,000. And our mini network is established using 3 sites: Belogradček and Rožen in Bulgaria, and in Serbia, our new astronomical station Vidojevica of Belgrade Astronomical Observatory in Serbia. Here you can see main institutions about that 3 sites, and we've got about 6 telescopes to use now. And you can see about their names and diameter of the main mirror. Plus, we can use from time to time Indian 1.31 RAS telescope, Manora Peak, Nainital, via cooperation with that few colleges there, especially Dr. Alok Gupta. And the main set of filters is Johnson-Cousins standard filters, and we've got also in cooperation with the Bulgaria side, in line with some institutional Academy of Sciences of both sides cooperation. We've got Gaia Celestial Reference Frame and the fast variable astronomical objects project during the 3 years. I'm the head from Serbia, and Dr. Rožen Bačev from the Bulgarian side. About telescope instruments, cameras, CCD cameras, I had a talk about it 2 years ago, but for some colleges who want to know about that instrument, 6 instruments, you can see the main positions, longitude, latitude, and altitude, also CCD cameras, and about the diameter of the main mirror of that instruments. Here we've got left side our main telescope, 1.4 meter, established since mid-2016 at Astronomical Station Vidojevica, our new site south of Belgrade in Serbia. And it's interesting that we've got possibility that for during this year to establish to remove 40 centimeter mid telescope, small instrument from Belgrade to Astronomical Station Vidojevica, and we've got now also some Polish dome cupola, small cupola for that small instrument. And we hope to start with that observation, with that, using that instrument during this year. Here we've got some table with the main information about CCD cameras, telescope, pixel size, scale, field of view, etc. And at that 2 pictures, we've got Schmidt camera in Bulgaria, Rožen Observatory, and 60 centimeter telescope also at Rožen Observatory in Bulgaria, Rhodope Mountains near the border with Grek. Belogradček Observatory also in Bulgaria. In the central part, you can see small cupola, small Belogradček Observatory in Bulgaria, south of Danube and close to Serbia border. And it's keep it with 60 centimeter telescope between that very famous Belogradček rocks. About some papers during 2020. We've got a few published papers together with Verikovsky et al. In astronomy and astrophysics about ice rock, which we observed 2.5 years. Also about Szegedi-Elek investigation of that very interesting object. A paper published in Astrophysical Journal last year. And I published it in Bulgarian Astronomical Journal about comparison of photometric results between Serbian and Bulgarian telescopes, one paper last year. It's our image of ice rock alert object using our 1.4 meter telescope of Vidovica. And about that object, we did it, as I said, 2.5 years, from 2016 until the mid-2016 until the end of 2018, and included two telescope, 1.4 and 60 centimeter, 1.4 meter and 60 centimeter at Vidovica, 2 meter Rosen, Schmidt camera also at Rosen, and 1.31 meter Aries in India. And you can see we did it with a lot of epochs points using 1.4 meter, it's near 300 points, 160 centimeter. Vidovica telescope by Rosen about 60 points, etc. And we started just at the beginning when that alerts was published. 7 members in our team were included for that observation. So Svetlana Boeva, Georgi Late from Bulgaria, Goran Damjanovic, me, Oliver Vince and Miljana Jovanovic from Serbia, and Gupta and Pandey from India, from that RAS Manora Peak Observatory. Another object, not too much points, but it was interesting for Szegedi-Elek investigation. You can see some main information about that object here, and our few points at the beginning of that, as you can see near the top of that alert, that light curve. And now our attention is on that object, interesting for some people in Lithuania, some colleges in Lithuania. We did that object at the beginning, 2019, using 60.
Goran, excuse me, 2 minutes left.
Okay, thank you. Using a 60 centimeter Vidovica telescope in August, and at the end of last year, four times in November, 2 times, and 2 times, and in December 2 times. You can see here that last year it was during the last year it was observed 11 objects, mostly using 60 centimeter Vidovica telescope, 1 object using 1.4 meter Vidovica, and no other instruments were included because of that problem with virus, but we hope during this year to continue our activity more than last year during observations. And conclusions, usually we did about 15 objects per year, but last year 11. And totally during 6.4 years, we did about 100 objects using that mentioned 6 telescopes in Johnson-Cousin filters, standard filters. And the thing is from 1 to 3.5 arc seconds mean about 1.2 at Vidojevice, but some nights with very good things about 0.7 arcseconds. At both sides, 2 meter Rosen and 1.4 meter Vidojevice telescopes. It's some information about images, CCD images. All in all, during that period from October 2014 until the end of the last year, we observed about less than 3,000 images, CCD images, and that about 90 objects. And we can observe the objects until 20 magnitude using bigger instruments, our bigger instruments, and until 90 magnitude with smaller telescopes. About some news, as I said, we've got for mid-2016 1.4 meter at Vidojevice, new dome 2 years after that, new under Cornell camera. Also at Rosen, the same camera from 2018. And we've got also that Andor camera, interesting for lucky imaging, for investigations of double stars, but we hope to adapt that camera for other objects. Aluminization at 2 meter Rosen, it was done 2017. And I hope that that 40 centimeter mid telescope at Vidojevice, it will be in operation during this year. And that's all. Thank you.
Okay, thank you very much, Goran. Unfortunately, we don't have any time left for the questions, so I will ask Justas to set up his screen. I will just say that Goran has been indeed, and his group, they have been actively operating with us even before Gaia alerts appeared, so from like 2013, the very early days. So thank you for this. Okay, let's move on to another country. Let's travel to Lithuania with Justas presenting Gaia alerts observation from there. Justas. We cannot hear you yet, Justas. Well, we did see a slide.
On my microphone. And when it's...
Now I hear you, but we don't see your slides.
Yes, because...
Okay, that's
when
better.
I show the slide, I lost the button when I can...
Okay, the floor is yours.
Okay, and I tell a little bit about our observation and reduction in Molėtai observatory in Lithuania. And in our group is some people, Marius, me, Erika, Vitas, Rimvidas, Ruta, and Ves Kotrina. And we observed already a few years. And this is picture of our observatory. Really, it is screen, it is shot from camera, and that camera we usually used when we need to decide it is good weather or bad weather in Molėtai, because we observed remotely. And in this project, now we usually use this small building and small telescope. And today, Molėtai look like this. And this is our small telescope. It is really very small telescope, and the camera was thermoelectrically cooled. It means operating temperature depending on area temperature. It wasn't so good for us, because small telescope and pixel size not very big, but one pixel is more than 2 arc-seconds in the sky. It is also not very good for us, and we worked at this project already 2 years. The first years we observed 52 nights, and this year we observed 150 nights. It is observed, it's from Gaia alerts, especially nights. I count only that nights that we observed for that project, to observe Gaia alerts. And this year we observed 37 objects. Some objects observed few times, and some objects observed many times. For example, alerts Gaia 20 BOR, we observed more than 70 times, and there is, I think, only other data from Multiepoch. And we can say that Multiepoch is quite to the north. And the star we can observe because the star was in the north. And the northern star we can observe almost all years. All year. So we all time see that star that is in the north. Many times we observed the star alert Gaia 19 DKE. We used for that star more than 100 nights in this year. And some example for our observation, which we observe at the most. And we always try to have the best curve that we can. And if this Gaia 20 CVU, we saw that it is curved, it is not one but few. It is a different observatory observed that object. And because it is a little bit wider. More observation, what we observed is Gaia 20 BLB or Gaia 19 DMG. And here also we saw the big scattering, like see the big scattering, but it is at that time the star was observed maybe 3 or 4, even more observatories observed. And it is has different level observation. And now I want to tell about some problem which we noticed during that this observation in that project. When we observed target Gaia 20 COG, and we can put the data to the server. And we asked Pavel put this data. He put some data, but we can put data which we observe in V filter at all. And it is because in that area of the sky, no A-pass catalog data at all, and it is no standard in V filter. And when we decide not observing this target in V filter because it is useless, we can put the data from that. Another maybe a little bit not bigger problem, but the problem which we can solve many times, and it is this point bottom to the curve, and we trying different methods how to avoid that this point. And when we noticed that when we using astrometry, sometimes they give a little bit wrong coordinates, maybe 1 second apart or half second apart from real stars. And this point is red, and here I think it is DKA star. And I just try to second time send this image to astrometry using internet, and then I give more correct answer, and that point is blue point. It is coordinate of stars. And after second sending the image to astrometry, we do photometry, and we have our point not in that area, but in a normal curve. It is, first, it is very good, but we noticed that it is problem not only in Moleti, and another observatory, which data are going in that area, appear in that area, and we propose you use the maybe same method than we use now. And the last half year, we don't have our points under the curve. It is good news for us. And as I mentioned, Gaia 20 or Gaia 19 DKE is the most observed star in Moleti Observatory. Just in the last year, we observed that star more than 100 nights. We start observed even early that star, and we proceed with observing the star in this year also. It is very good news for us. Also, we take attention to the flat field when we observed.
Just there's 2 minutes left.
Okay. I used I like to say one standard flat field, and when we give new flat field, I always compare them. It is like the same, because it can be some, when we observing remotely, we don't, sometimes we can notice the small clouds, and it can be that our flat field will be bad. It was bad because of cloud, or maybe telescope will go not directly, not in that direction when we want. And it also, we notice that it is also help to have a good result. One more thing is that because we're using thermoelectrical cooling of CCD, we notice that after flat field was done with that CCD camera, we can take dark images. It is a very big level of dark images. And after we take the flat field, if you want to, after that, take the dark images, we need to wait maybe half an hour or 1 hour, and only when we can take the dark image. It is can be good. And it is all.
Okay, thank you very much, Eustace. Are there any questions to Eustace? I just wanted to emphasize what Eustace said, actually, that given the north localization of the Multiepoch observatory, they can observe targets for a very long time, which is quite a good benefit. And surprisingly, they have quite a lot of clear nights, as you could tell from the longevity of their light curves. So that's been a significant contribution to the follow-up program. Okay, since I don't see any questions, let's move on. We now have again a series of very short poster presentations. So in total, you will have 5 minutes for presenting and discussing, and we'll start with Ruta. Please share your screen.
Hello.
Hi.
Can you see my presentation?
Yes, it seems fine.
Okay. So, hello once again. I'm Ruta Urbanavičiūtė, a first-year PhD student from Vilnius University, and today I will tell you a little bit about variable stars in northern sky. So, my master thesis was about searching new variable candidate stars. Observations were made from Lithuania Molėtai Astronomy Observatory. There we observed 5 fields near North Pole, in which we analyzed about 13,000 stars, from whom we found 20 new candidate variable stars. There were long period, short period, and binary stars. After that, I decided to continue research in binary stars with variable component for a PhD thesis. So why binary stars with variable companion? Large fraction of the total stellar population consists of binary and multiple star systems. Binary systems allows determination of stellar properties such as mass, luminosity, radius, where with single star observations we cannot do that, or it's quite difficult. They also are important for studying gas dynamics, accretion processes. Further, binary stars better explain astrophysical phenomena. Astroseismology methods can tell us inner structure of the stars, and when we combine the best from these two worlds, we can better understand stellar evolution, compare these models to existing ones, and improve them. So, what's next? We want to examine all known binary type algo stars and look for with variable component. If we get lucky, maybe we find new binary stars with variable components. One of the example of the stars, this TIC stars you see in your displays. This system was found by my advisor Erika Pakštienė, and now the star is researched by teams from Vilnius and Aarhus University. We can see from the light curve that binary systems temperatures are quite similar, systems are eccentric, and we can see even tidal effects. So in the right, we obtain spectra of this binary system. In the left, we can see measured radial velocities, and there are some preliminary results combining light curves and radial velocity curves. We can derive such parameters as effective temperature, surface gravity, mass, radius, density, orbital semi-major axis, orbital period, periastron axis, eccentricity, H. And in the lower table, there are parameters from spectral analysis. Its effective temperature, surface gravity, velocity. And with this information from these tables, in the right, we can see a chart diagram. And I don't know if you can see my pointer or mouse. Upper black star is a variable star in the system, probably Delta Scuti star. And this star is probably main sequence star. And open circle is from Gaia values. And here we can see there are not just one pulsation, but more pulsations. And it's definitely binary star with variable component. And also I want to thank Lithuanian Science Council. Thank you.
Okay, thank you very much, Ruta. There is a question from Marius.
Okay, Ruta, so I have for you a very practical question. So if variable star somehow accidentally appear in the Gaia alert list, it is, how can we simply recognize it and distinguish from gravitational lens event?
Gravitational lensing light curve will rise and then go down. But with binary stars, we can see first light curve is going down and then rising up.
All right, thank you. I hope it satisfies Marius. Thank you, Ruta. Let's move on to another brief presentation.
Yes, thank you.
Thank you. It's Algita Stankiewicz from Warsaw, please.
Hello, everyone. Just a moment. I hope you can see all my slides.
Yes, yeah? We do. We can
hear you. So my name is Algita. Hello, everyone. I hope I will just skip my first slide just to save a bit of time. So to begin with, I'm working at the University of Warsaw. I'm a third-year PhD candidate. And last year, even during the pandemic, I was unable to work quite a little bit with Max Planck Institute for Astronomy. Here you can see all my team members that I've been working with. So I'm gonna tell you with a very fascinating, instrument. It's Mikado, and also very fascinating future project, which is called Extremely Large Telescope. So briefly about it, it will be the biggest eye on Earth, hopefully in 2025, because the primary segmented mirror will be around 40 meters in diameter. The whole system will have 5 mirrors, 3 the main, and 2 mirrors will be used for the adaptive optic systems. Adaptive optic systems, are enabled to eliminate atmospheric distortions. So that's why they are very important parts in the modern astronomy. So here you can see the whole Mikado. Mikado is a multi-adaptive optic system. Here you can see it's not only single conjugated SCAO, but also it has multi-conjugated adaptive optic system. And it's not only imager, but also a spectrograph. And what's the main features that it will provide? The angular resolution of, let's say, 5 milliarc seconds. So there will be a very precise, let's say, observational data. So the main thing that I was working with was MCA, is called the calibrational unit. So calibrational unit, how to say, important feature is that if the calibrational unit works properly, so it means that the whole instrument, how to say, are enabled to work. So the best thing is that how to say, to have a proper calibration, so you can see the performance of your instrument. So here you can see Mikado calibrational assemblies, let's say, setup in the laboratory, which has a Fabry-Perot etalon. Why is we use Fabry-Perot? Because it's a single mode fiber. It has a continuous spectrum, also superluminescent emitting diodes. We use H and K bands, and we use so-called FTS. FTS is Fourier transform spectrometer, which provides the emission spectrum. And of course, we use the fiber collimator, which how to say that we manually can collimate the light beam. So as our research like stated that how to say, the Mikado will be enabled to gain 5 times greater resolution than a conventional 8-meter telescope. And of course, in sensibility, almost 125 times. So it's very, how to say, it's very unique instrument. So we took the spectrum of Fabry-Perot etalon, and here you can see it produces some sort of slight peaks. We are not interested in this part because it's just additional noise regarding the peaks. We are mostly interested into the peaks. So we fitted them with a Gaussian function, and we calculated the free spectral range. And here you can see from the free spectral range that how to say that it's a linear. So it means that our our calibration was good enough. With sleds with superluminescent diodes, because normally the light source degrade over the time and also environment temperature. So we took around 30 emission spectrums of the light sources, and we calculated how we degrade during the time and the temperature. So here you can see at the beginning it's a bit degraded because it's not lighted up enough, and sometimes also it degrades during the end of your performance. The same with the K-band, just in the middle of our operating temperature. In conclusion, I would like to add that the further research will be to calculate from Fabry-Perot wavelength drift. So with a wavelength drift, we can estimate radial velocities. So I'm still working on it. So I can tell you, like, our primary results that our wavelength drift is only milli nanometers, so it's very light drift. So it means that radial velocities will be enough to have a proper sensibility and resolution. So that's why we can be able to model how our images will look like, and how we can detect, for instance, let's say black holes, because it's my specialty, and we can estimate how many details we will get from those images. So that's my end of the talk. Thank you so much.
Thank you very much, Elgita. This is potentially a new avenue for the younger astronomers in the next decade to observe more alerts in high resolution. I'm afraid we have to move on. Thank you for this. So if you could stop sharing your screen, and now if we could have Karsten sharing his screen.
Yes, thank you very much. I will go ahead.
Right. We see you, we hear you.
Good.
Please.
Hello, everyone. My name is Carsten Brogaard. I work at the University of Aarhus in Denmark. And today I will be presenting a new educational telescope that we're setting up in Australia. The reasoning behind this is that this is a new telescope and it's only meant to be used for teaching upper secondary schools in Denmark. And the idea behind all this and the idea of setting it up in Australia is of course that they should then be able to observe in Denmark during daytime, which is then when they have their regular classes. And that's the whole idea behind this. So the telescope is already set up and it's in place. So I just had a few images, one of the telescope and one of the telescope in the dome. It's the one on the left here. And it's located at Mount Kent Observatory in Australia. What we're currently working on is then, of course, the whole backbone of the remote control of the telescope, because the idea is that all the upper secondary schools should then be able to control the telescope just using a regular browser. So we need to set up, of course, not only the backbone, but also the web-based control panel. And of course, then along with that comes also an archive for all the observations and a lot of teaching material so that the upper secondary schools can actually use this for teaching purposes. We're not as far along as we would have liked to be, so we are hoping still that we'll have them ready for the next school year starting in August, so that they can actually start using it for real at that time. And the whole reason that I'm here presenting this and I've been joining this workshop this week is that I'm hoping to use the BHTOM and the calibration server behind it, in a sense that, well, it's not me that's going to use it, but maybe this can actually be set up so that the Danish students can upload the images and actually see that some science comes out of this without having to have a lot of experience in actually how to treat the data in order to get them to the level where you can do science. Yes, that's actually all I had. So now I'll take questions if there are some.
Great. Thank you very much, Karsten. Are there any questions now? I think I'm very pleased that you joined us. I hope it was informative, and I hope we will eventually make it work. That was also the idea, to have the CPCS and BHTOM to be used by people who have no idea how to process the data. So we hope you will be our guinea pig to test this on students.
Yeah, I'll certainly look forward to doing that. Exactly.
Great. Definitely, we should do it. So thanks for presenting this. Okay, I don't see any questions, so let's move on. Thank you. And our penultimate talk, actually, there has been some changes in the schedule, is also about education and use of telescope networks in education by our long-term collaborator, Fraser Lewis, please.
Hi, Rukesh, do you hear me okay?
Yes.
You can see me, see slides.
Yes. Mm-hmm.
Fantastic. Yes, I represent, I guess, 3 separate organizations that are in some ways also providing guinea pigs in the way that Karsten was describing. So yeah, I've worked with Rukesh, Simon, and the Gaia team, I guess, for, I don't know, 6, 7, 8 years, perhaps even. I'm part of the Fulks Telescope project, which is in Cardiff, in Wales. I'm also part of the National Schools Observatory, which is based up in Liverpool, looking after the education, sort of the link between education and outreach that the Liverpool Telescope people do. And I also work for the Open University, again, a distance learning provider and another owner of robotic telescopes. So just to give you a little sort of indication without going through all the politics and all the technicalities, I work with the Fulks telescopes that have access to the 2-meter Fulks telescope north and south, which are in Haleakala in Hawaii and in Siding Spring in Australia. Liverpool telescope, not surprisingly, isn't in Liverpool. It's in La Palma in the Canary Islands. The time that we have on the telescopes, the time that we use within the Fox Telescope project is part of the Las Cumbres Observatory network allowance that we have working with them, and access, of course, to their 1 meter and 40 centimeter telescopes, and in fact access as well to the spectrographs, but that's a story perhaps for another day. We've created over the years, I say we, in this case, this is Sophie, who was our PhD student at the time, who's now a postgrad and working with us on postdoc, I should say, who's working with us on a variety of projects. She created a series of these background material sort of handouts, 4 or 5 page PDFs, all in English, I'm afraid, but looking at the different aspects of the science that Gaia does. So not just looking at the astronomy, the astrometry and photometry that we've been talking about this week, but all the various aspects of the technical and engineering sides of the mission as well. There are a couple of links there at the bottom. Again, if you missed the links and you want to find out more, then contact me. I'm more than happy to point you in the right direction for those. I don't have any new results to report this year. I'm kind of an imposter in that sense in the conference. I wish I did have some more. I was going to say it's been a tricky year. I think that's probably taken as read for all of us. But yeah, we've not really been able to produce any new resources with students this year. However, we did see a talk yesterday by Yaroslav who explained about Gaia 18 AEN and its symbiotic nature and how he was able to use the Gaia data to produce that. There are a few names on this paper that you may recognize, people that are at the conference this week. I would draw your attention to the 2 in blue that I've marked there. Megan Greet is a teacher in a London school, and Jorgen was her student at the time, I think about 16 or 17 years old. They both worked with myself, with Simon, with Wukash on looking at data and taking data of Gaia objects. They took some data of this particular target, and we were very pleased when in 2020, Yaroslav was able to publish this paper and include them as authors on the paper. They're, what are they, 15th, 16th author? Not a big deal for us as a scientist, but as a teacher and as a student, that's a really, really big deal. We will try to produce, or we will be producing a news article on our website to sort of highlight this, and we'd encourage you, if you see that via social media, to share that with your people as well, because that's a really nice result. It's a bigger result for us in terms of education than perhaps it is in terms of the science, if that's fair to say. I will mention this as a particular resource that I've produced. It's not related directly to Gaia, although we did hear about Hertzsprung-Russell diagram on a few occasions today. This is an inquiry-based science education project. So it's an extended project or a teacher-free project, which I created a few years ago based on the Hertzsprung-Russell diagram, based on taking real data from Fulk's telescope of open clusters and using the photometry to create Hertzsprung-Russell diagrams of real data, hopefully with the idea of persuading students to then go on and take more data of their own, create their own sort of ownership of their own data. So we've been successful in this. We've created a few of these different resources now. They all exist on the National Schools Observatory website. They are all free of charge. There is no requirement to pay for it, to pay for any of the resources or to pay for any of the tools that we provide or suggest to use these activities. In the case of the NSO, we do ask for a password and login, simply because we can kind of track what people are doing and how they're making progress through the activity. So we're being a bit Big Brother-like, but it's hopefully to sort of produce, for us to understand those resources better. This leads me on to the other new one that we had. We had some funding at the tail end of 2019 to produce an activity on supernovae, which we did using again, the NSO website. We're using data on type 1a supernovae. We provide about 20 pages of background material. You can see the web links there towards the top of the page. This includes doing photometry, in this case using an online browser, so getting rid of that horrible idea that you have to download all your software onto machines. We produce Excel sheets as templates on how to analyze that data. I suspect most of you know all this, but you can calculate from a type 1a supernova its peak brightness and use that to put another data point on the Hubble plot. And from the Hubble plot, you can calculate the expansion of the universe and the age of the universe. Again, bear in mind, we're doing this for 16-year-olds, but we're getting them to do it with real data. We hope to then persuade students to use either Gaia or, of course, the LSST, which is coming online in the next couple of years as well, to find their own objects, to collect their own data, use that data then to create extra data points on the graphs. This is essentially what you get when you do the Hubble plot. You get a measurement, you measure the trend line, and you get the measurement for the Hubble parameter in horrible set of units, as we all know. So in the case of doing this, what we've discovered is that we kind of need to help the students with something like Stellarium to understand what is in the night sky. Maybe they can do that using Python, bits of Python code as well. So again, we can use computing as well as just plain astronomy skills. The data analysis can be done via free photometry software, and we provide Excel sheets or Google spreadsheets to then sort of collate that data and transfer it into something that's very, very meaningful. We think this provides our students, and in the case of this one, with it being citizen science type project as well, we think it shows them the scientific process, how you go about collecting data, how you go about analyzing data, how you report that data. And in the case of the big data sets, and we see this with some of the Gaia targets as well, you know, there's a real true collaborative nature of the work that scientists do, and we can sort of get the students to understand the spirit of that. We can trick them. They might not realize it's maths, but we can trick them by astronomy into understanding periodicity, into understanding trend lines, logarithms, error bars, all sorts of things like that maths teachers would be really happy for us to be sharing with these students. And hopefully, finally, we can persuade the students to create their own projects. There are lots of hurdles. Carsten, I don't want to put you off at all. And hopefully, if I share with you the hurdles here, then you can maybe swerve a couple of them. They often require a lot of background information. You know, if you want to do supernova type 1a and cosmology, you're asking a lot of 15, 16-year-old students to understand that. So there is the idea there that we have to provide lots of background information, but we don't want to give them so much that it kills the joy, kills the spontaneity. Installing software is often an issue. Getting students to understand that they don't just end up after an hour with the answer is 12 and they get a little tick and they go home, you know, to understand that there's more to some of these projects than just doing that kind of very basic learning that the younger students particularly are more used to doing. Sample data sets we can control. Real data makes things more difficult just because it's real data and it doesn't behave the way that we might hope it would. And again, just a note there from Yaroslav's paper, that was data we collected in 2018. That was published last summer. That's no criticism of his group or of the way that we work. That's just the nature of how science works. It takes maybe a year and a half, 2 years. For students who are 16, it's difficult to keep that inspiration up over that time period. They've sort of moved on quite a lot in their lives in those kind of timescales. Where next? Well, this is where, again, hopefully there's a little bit more good news in terms of Gaia alerts. We have a little bit more money, a little bit more time available with FT to try and promote these kinds of projects and develop more of these projects. In a couple of emails with Rukash, it's obvious that BHTOM is a very powerful tool in being able to upload FITS files and do some of that horrible legwork that the students might not enjoy. You know, to produce automated versions of that. I think that's kind of useful. And we're hoping to develop more of these types of projects. If any of you have any ideas of the types of projects you'd like to see or you'd like to work with us on, then please do contact me. The next ones will probably be around the themes of variable stars, compact objects. I think it was 2 talks ago we had someone saying that black holes are the most exciting objects in the universe. I fully concur with that, absolutely. So that's something we want to try and do. And also maybe to work on spectroscopy. So not unambitious, but you know, if you don't try with these things, you will never succeed, I guess. Thank you very much for your attention. That's my contact details if you want to get in touch. Thank you.
Excellent. Thank you, Fraser. for this encouragement for us to keep doing what we do, and this impact we might have thanks to you. Otherwise, our efforts would just get, buried in some obscure journals. And thanks to you, they get to see the world. Are there questions, comments to Fraser, please?
I have one, if I may.
Yeah, Karsten, please.
So it's more of a general kind. It's just it would be very nice if you might want to share your presentation on Slack or one of the other platforms, because there were many links in there that I would like to have a look at.
Sure, I can email. Yeah, email me and I can email it over to you if that's easier. But yeah, we can sort that out, no problem at all.
That's very many interesting things.
Yeah,
for me certainly.
Good.
Actually, yeah, we will try to gather all the presentations from everyone. I didn't say that yet, but we will, if possible, if everyone agrees, then they will be made available. I will remind you that the YouTube recordings are there, but scraping the text from YouTube videos, it's not what you want to do. Okay. I don't see any more questions, comments, and we have our last speaker ready, Agnieszka Słowikowska from Toruń University, who's going to tell us at the very last talk. Agnieszka is going to entertain us with planets with Gaia, please.
Good evening, to all of you. It's my pleasure to close this conference. However, I have only 3 minutes, so I must be fast. I'm Aga Słowikowska from Nicolaus Copernicus University in Toruń, and I'm going to present you a few slides that are results of cross-matching exoplanets archive with Gaia DR2. And you can see on the right hand panel the HR diagram, where we have, of course, the absolute magnitude G and BPRP. And with the colors, we indicated the host stars of exoplanets that are discovered with different methods, with transient, radial velocity, and imaging. As you might know, there is more than 4,300 exoplanets confirmed and confirmed today. And also, we know that with Kepler and TESS, almost 80% of them are discovered by transient and only 20% by radial velocity, and just a few with different methods like microlensing, imaging, or TTV, so the transient timing variations. And here what we have, we also wanted to compare the effective temperature of the host stars derived from Gaia DR2 with the temperature, effective temperature that was given in the exoplanets archive from other surveys. And here you have comparison, and of course this blue spread for the transiting planets. They are most likely the artifacts coming from the resolution of Gaia. On the right panel, you see the you have the planets as a function, mass of the planet as a function of semi-major axis, but also with colors we indicated the mass of the host planets. So you can easily see that the most massive planets are orbiting massive stars. And also with the different symbols, we indicate different methods of detection for the exoplanet. And here we have the planet's radius to planet mass, and with colors on this panel we indicate the ratio of the planet of the mass to the host star mass. So you can see here also with colors how does this distribution look like, and again with the different symbols we have different methods of the detection. And on the right hand side you have the planet density distribution. Of course, for the transiting exoplanets it's easier to determine the radius to get the density. And you can see that only for in a few cases of radial velocity, it's possible to measure the mass and the radius. Regarding the orbital parameters, I think on the left we have very nice plot that shows the number of planets in the system as a function of eccentricity. And also with the color bar, with colors, we indicate the mass of the planet. So what it shows that if we have more planets in the system, then on more circular orbits they are. And I think it's a very nice plot for, especially for students, when you talk about the evolution of the planetary systems. And here we have the eccentricity as a function of semi-major axis. And again, you see the strong distribution between the transiting and radial velocity planets. And also with the lines we indicate the iso-curves with the constant center distance. So this is how the metallicity of the stars looks like, depending on the method of discovery of the exoplanets. And there is tiny indication that the host stars around which the planets are discovered through transients, they have on average a bit less. They are less their metallicity is closer to 0, whereas for the radial velocity the peak is around 0.2. But of course, we need more data to confirm the statistics. And the last slide probably is the most important, because we were quite surprised to see the distribution. If you plot the histogram of the ratio of the mass of the planet to the mass of the host star, you see this bimodal distribution. And what is more, this distribution is for both types of the methods of the discovery of the planet. So the same, well, they're seeming the same. There is a tiny shift between them, but you can see that it's also, this distribution is also for the radial velocity as well for the transient. And you see that in between there is this mass gap. So the question now is if this is the similar gap as the famous brown dwarf gap. So if we have this planet mass gap to put the question, and probably I will close with this question, my presentation. Thank you.
Okay, thank you very much, Agnieszka. Are there any questions to Aga? I don't see many. There is one. Nikos, please.
Hello, Aga. Very nice presentation. Nice to see you also. I'd like to ask you, you've showed that different methods provide different statistics for several of your results.
Sure, of course. I mean, some of the statistics
and
might
why
be...
is this?
Well, I mean, it's like, you know, it's much easier to find the transiting planet with the short orbital period, right? Which is because of you need, if they have a big semi-major axis, then you would need to monitor the star for a long time to get the transient. And of course, it's regarding the radial velocity, it's easier to find the radial velocity variations if you have more massive star than if you have more massive planet than if the planet is like, let's say, Earth mass object, right? So it's very some of the statistics are strongly method biased, right? So you have to be, in this sense, you have to be careful. That's why the last histogram that I show, it's nice because it looks like no matter which kind of method you have, you still see this bimodal distribution. And it was kind of surprising for us. And also, I'm sure that regarding exoplanets, Gaia DR3 will bring a lot of new results from the astrometry, because you have many circumbinary orbits exoplanets. So the exoplanet that orbits the binary system. And for the moment, we claim that there are planets around based on the timing variation of the eclipses. But of course, the astrometry from Gaia will bring the like kind of final contribution, confirmation to that. If this is a planet, if this is the effect, the O-C variation that we observe, if this is caused by the third or fourth body in the system, or if this is completely connected with the physics in the cataclysmic variables, for example. So there is quite a lot of different stuff that one has to take into account while analyzing this kind of data.
So you would say that different methods basically probe different kinds of exoplanets?
In a sense as well, because you can see here that you have, with the transients, you have planets which are less massive and which are closer to the host stars, because it's easier to detect, whereas for the radial velocity, it's easier to detect, of course, you know, big hot Jupiters, which are massive, and then it's easier to find them in the radial velocity by the method.
Thank you.
And again, for imaging, for example, right? If you go look here, the squares are for those planets which are the farthest from the host stars, because then, of course, it's the easiest to separate between the light of the star from the reflected light of the planet, right?
Thank you.
There is a quick question from Chris Rybicki as well. Chris?
Thank you. Hi, Aga. Just a quick question about this eccentricity plot you have shown. You think this is the real effect or rather observational bias?
You mean this one?
Yes. Because it looks like a bias to me.
No, it's a real effect because you will have them due to the dynamical stability of the systems, you will have them on more circular orbits, right? Because
Okay.
look, I mean, if you have more planets in the system, apparently you need them to be on more circular orbits than if you have them, let's say, there is a system where you have the host star and the single exoplanet.
Okay, thank you.
And there is also a comment from Siegfried, and actually that is what I also wanted to comment, is that microlensing is not much represented in there, mostly because microlensing is probably still giving the smallest number of planets, so the statistics are probably different, but there's also a different method, right?
Absolutely. As you can see here, microlensing is 2.5%. And it's like, you know, 80% is transient and 20 is radial velocity. And then just a few of them are discovered by different methods, other methods.
But it's still something like 50 detections already, I believe.
Sure, but over almost 4,500, you are still, the statistic is still low, right?
And peculiar parts of the parameter space too, that's important,
Yeah.
Regarding microlensing, with the alerts, we already have one candidate planet within our alerts. I think it was shown by Etienne the other day. So that's another prospect. Of course, most of us here are mostly interested in black holes and long-term monitoring of microlensing events found by Gaia in particular. However, there is also a prospect, especially these days, with high cadence observations from surveys we've heard about today and earlier. Then we can find planets with the microlensing method, also with the Gaia alerts. So that's another interesting, probably, incentive for people doing the follow-up. And I see another. Well, there is gonna be extremely quick question from Mateusz now.
Yeah, just regarding the microlensing exoplanets, which you talked about just a second ago. Isn't it also a problem that microlensing exoplanets provide very little information about the planets, mass aside?
Indeed, and also, I mean, it's like event that will only happen once, right? So you cannot observe it again, and so you cannot like revise your parameters that you obtained from the previous measurements. So it's I think it's also kind of will be, you know, of course we have those planets, but it's hard to get the radius of this planet.
Okay,
right? You can get the mass, and you can assume that the mass is spherical distributed. So this is the most that you can get, right?
Okay.
Yeah.
Okay, I will leave. I have to cut it here. We will have more. We can have more discussions. But thank you, Aga, for inspiring us on this topic at the very last talk. Thank you. And so before we all go and have wine by ourselves or maybe together, hopefully I remind you that there is this social meeting at Zoom. I hope we can have not Zoom. Sorry, WonderMe. But before that, I will not let you go. Before me presenting something, I have to stop you.
Okay, sure.
Yes. And let me share a couple of slides just to wrap up the meeting. So I hope it will work like this. And when I hit this, can anyone tell me if you can see my slides instead of my...
Yes, we can.
Yes. Okay, good. So that's the poster, so this is the end of the 11th Gaia Alerts workshop, which we held online. And I'd like to thank all the organizers listed here, people who contributed to different aspects of organizing this. There is no one to thank for the catering, for example, like we normally do, unfortunately. Well, I hope you were all well fed, either by yourselves or by your family. So I think it was a great success from my point of view in terms of, at least, the technical point of view. It worked well. I'm surprised we didn't have any major problems with that, but also scientifically, I found it extremely interesting and amazing. And we had 110 registrants from around the world. As you see on this chart, we had people from all over the places. Fortunately, there was not a time that we had all 110 people connecting to Zoom at once, because I think my subscription to Zoom would not handle that. So, but I think most of those people were present at some point during the workshop, and we had about 60 talks. This is quite amazing, and a large variety of talks. The talks were recorded, almost all of them. And they are immediately available now. They were streamed live, but now they will be. This is our place where we keep the recordings. So if you go to the workshop page where the workshop agenda is, there are where the timetable is. You have all the links to YouTube. There is also this shorter version of the address, tiny URL, GSO 2020, and I've noticed that the YouTube videos, even though at live they were observed by something like 10 or 20 people, in the last few days they got more than 100 views already. So it could have been you, or this could have been other people as well. So I hope we make a mark in the community. So now I will spend just few slides doing my own subjective summary, very subjective, so forgive me, just going through all the days and highlighting some things, and of course every single slide, every single presentation was a highlight in a sense. I'll just emphasize a couple of them I found interesting. So on the first day, we had a summary of Gaia activities, Gaia, how it performs, and the generic Gaia alerts talk, and then all the politics related to OPTICON and organization of our work, especially the networks, both from optical and radio perspectives. And then we talked about Black Hole Tom. This is just a few snapshots of Timo, Jerry, Simon, and Pavel. We introduced the Black Hole Tom. That was one of the major steps for us during this workshop to have the Black Hole Tom running for for Monday, so that then people can access it and start using it. So there was an increased activity on our side in the last few weeks to make it live and running. And I think we survived, and hopefully it will be used from now on. Then moving to this next day, we had talks about machine learning and classification of the alerts. Then we talked about infrared observations as well. And then we talked about other surveys like plant surveys, large array survey telescope of Iran, and OGLE, and Poznan telescopes. Just a few slides here showing slides from Ilknur that we find those crazy contaminants, which they look like microlensing, but after a few months, they turn out to show very different behavior than microlensing. So we're trying not to waste time. I hope I don't offend anyone. But if we are interested in microlensing, we would like to find out as early as possible. Random forest and the other classification methods were presented by Alexander, and there were other approaches to classification of alerts as well. Here's another slide from Maria Gabriela, showing microlensing events in infrared. This has been happening, but I hope it will be also future for microlensing. In particular, infrared is a very new avenue. And then I mentioned already Eran's talk about his amazing, efficient, and cheap all-sky survey telescope. Wednesday, again about Gaia, other activities within Gaia consortium, but then we focused on microlensing primarily, and here are some slides, and I was particularly impressed by Dirk's and his network of telescopes and people collecting beautiful data for many years. And I hope it will continue, and we will also benefit from it in our scientific region. Then some candidates for beautiful microlensing events where the follow-up was crucial. Without follow-up, we can't do much, and with the follow-up, we can learn much more about the lensing events. And eventually, I hope we will find that lensing black hole among our alerts. Thursday, we moved out of the galaxy mostly. There was a mixture of talks, but primarily they were mostly about tidal disruption events and other types of transients, in talks by Yair and then Morgan, showing how Gaia can be used also in the aspect of looking for companions to former supernovae. Then we had talks about polarimetric observations of AGNs, the new instruments, very huge, showing huge potential for a very interesting science with the alerts. Also, we've seen Gaia itself as on an image of RT, and in the presentation of his amazing the observatory and refurbished 2-meter telescope located in Europe. So that's a way to go. Friday, we just finished this session with Gaspar presenting his Headbuy all-sky telescope with extremely high precision photometry, and then other telescopes presenting their follow-up. And then I wrote it down that we need to produce more papers, all of us, not only on microlensing, but on the other stuff. And so far, we've had 2 highlighted here by Josep, but we should extract more. Now we have the data, we just need to process it. As you see, the follow-up examples of Eustace, there's a lot of data. There's many things we can do. We just need to sit down and publish. And I do encourage people to step up and take over. The data is available, and we should collaborate together on these papers. And very impressive data collected by the AFSO group represented here by Stephen. Okay, so just to wrap up, I would like to make some points. What's next? So watch the talks, the recordings, if you missed something. Then share your PDFs, as I already mentioned. Please send me the slides if you please, so that I can make them available on the workshop webpage. And then keep in touch with each other, with us. There is this Slack workspace, mostly dedicated to Black Hole Tom activities related to this, but also to the follow-up observations. So please join there. You have all the links. If you don't have the link, you lost it somewhere, then get in touch with me. Observe, right? That's the main thing. Observe and collect the beautiful data as you did in the past, and then use Black Hole Tom. Provide us with the feedback, make it crash. Which will make us happy if we find mistakes and errors in it. But we do want to make this tool useful for everyone. And write papers, right? I mentioned it already. Certificates of attendance, you will receive them via email if you requested one in your registration form. They will state that you were here and we certified this. And the last note is that we hope to have another Gaia Alerts workshop, the next one, to happen summer, autumn. We'll see how the situation develops this year, 2021. I don't know if you noticed that this workshop still carries the name of 2020. That's intentional. We still hope to have our 12th workshop in 2021. So stay tuned for this. And I will stop with this slide advertising the link to Black Hole Tom and the Black Hole Tom email address, generic email address. And I hope we will keep using this tool later on. And I will stop here. I can take questions if you have any. Stop. Yes. Questions, comments? If not, then we can move on to Wonder Me and have a social time. So thank you all.
No questions for Kash, but I do want to just say a word to thank you very, very much for organizing this, all your hard work, and I'm sure you had a team helping you. Although sometimes I'm not sure, I think maybe you take it all on and make it all work. So thank you very much for organizing such an excellent meeting, which was 5 days, very well balanced, very exciting science, and good input, and so many great talks. Thank you very much for everyone for their great talks.
Thank you, Simon. Yeah, thanks.
And I will also see you on Wonder.
Yes, let's go to Wonder. Bye, everyone.
Bye-bye.
Bye-bye from John.